Good evening, sir.
Good evening, sir.
Good evening, people.
Good evening, sir.
Good evening, Guruji.
Good evening, everyone. So, let's continue with our last chapter that's ongoing. That's applications of Schrodinger equation. And yesterday we had started with, yesterday we completed the boxes and harmonic oscillators. Everything was done related to them. But I told you that I wanted to take some questions on anisotropic oscillators also. So that will take, and also a couple of more questions on the general, like random questions, basically to oscillators also. So let's just take one question.
I have a doubt.
Sure.
I have a doubt. That's my question. थोड़ा सुनिए. The orthonormality wave function psi1 and psi2 corresponding to the ground state of a fast excited state of a one-dimensional potential.
Okay, so this is ground corresponding to ground state. This is corresponding to first excited state of 1D box.
Yes, sir. Psi1 and psi2 are wave function, ground wave function.
Okay.
And sir, given a operator a cap, x on the wave function, that a cap psi1 is equal to psi2. Okay. And a cap psi2 is equal to psi1. Okay. Sir, ये चार ऑप्शन से दो एक पता चलता है ठीक में. चार ऑप्शन है सर. Which of the following statement correct? Okay. The expectation value of a for the state psi is equal to 3 psi1 plus 4 psi2 by 5. Okay. Is 0.96. Okay. And the second option is sir, the expectation value of a for the psi is equal to 3 psi1 plus 4 psi2 by 5. No, I'm not getting. Wait, this is for which one? This is for which one? Yes, sir. ये कह रहा है कि दोनों केस में
अच्छा, okay, correct क्या? नहीं, दोनों केस है which case? अच्छा, okay, for ground state and for first excited. Then I'm not getting the question I got now. Okay, मैं लिख के भेजता हूँ. Okay, मतलब लिख के भेजूँगा कहाँ पर भेज सकते? Chat box में बड़ा हो जाएगा वो. हाँ, so but see, because what saying? You want to share the screen? I can give you an option.
Yes, he can share, sir.
No, I have restricted that, but wait, one participant and I want sharing. Okay, as of now only host can share. Now I will just allow all participants. Okay, so try sharing. You can share the screen. Sorry. Last week, नहीं दिखाना है. Today is his birthday, by the way, if you are aware of. Today or yesterday? I think it is today. Maybe it was yesterday. Today only. Right. We are not yet able to see anything. I don't think in screen sharing they will allow us that option. You have to take a screenshot of that, but I think screenshot also won't be allowed. Okay, so you do only mail me the question, and if I feel that the question is good enough, I will take it in the class tomorrow. Okay. Sure. Next. So anyway, let's continue now. What did we start with? Okay, so I'm just taking a question, random questions we have been taking. So for 1D harmonic oscillators, okay, they have given us that wave function is given by 1/√2 into psi1 plus psi2, basically psi1 of x and psi2 of x. Okay. And they're asking us the average energy is. Okay, so we already have the formula for average energy. Please remember that's basically probability that the particle will have energy E1 into energy E1 plus probability that the particle will have energy E2 into energy E2. So that's what we want to find. But we require respective probabilities and respective energies. So first of all, we need to expand this 1/√2 psi1 plus 1/√2 psi2. First of all, you can write this if you want C1 psi1 plus C2 psi2. Okay, now the value of C1 is 1/√2, the value of C2 is 1/2. So is it normalized or not? It's clearly not normalized. C1 square plus C2 square, that's 1. But anyway, it doesn't matter. What is the formula of probability, people? Probability is given by C1 square upon C1 square plus C2 square. But please remember that we are writing square just in case if it is complex, you have to write C1 star C1 if it is complex. Anyway, C1 is real, so don't worry. So we have 1/√2 square, that's 1/2 upon 1/√2 square plus 1/2 square, that's half plus half, which is 1. So probability of E1 is half. Similarly, probability of E2 is also half. I'm rushing through this because I'm expecting that you are comfortable. So you can also tell me, let's re-explain. Okay. So I hope you understood probability of E1 is half. Similarly, probability of E2 will also be half because both are anyway 1/2. Okay, that's also done. Now what about energies? It's 1D harmonic oscillator. So in harmonic oscillator, the value of energy was n plus half h squared omega. So value of E1, that is basically, they have to clearly mention in the question right now, it's not mentioned whether one is ground state or excited state. So that they have to give us now. So I will mention that psi n, or let's say psi n is basically an excited state. That I'm giving you, okay? That they have to give us whether psi n is ground or excited. Okay. So because they have mentioned that n represent n excited state and it's not nth level. So psi1 is first excited state. For ground state, if you remember, n was 0. I repeat, for ground state, for harmonic oscillators, n was 0. For first excited state, n is anyway 1. Or I can make it complicated. I want to make it complicated. First, copy this first, and let me give you that. Let's say psi n is wave function corresponding to nth level. That's better. A bit more complicated. Wave function corresponding to nth level. So write it psi I. Psi I is wave function corresponding to ith level. That's what you do. I'm purposely making it complicated. Okay. First, please copy this. Take your time. Probability is half of that. I hope it's understood. You can always tell me to repeat the explain now.
Yes, sir.
Okay. Others? Anybody's writing? Let me know. Sure. So now that I have given you psi I is nth level, they have given us psi1 and psi2. So this is first level people. It's not excited state. When it's first level, it means it's ground state. Okay. And since they mentioned this is level people, so this is second level, it means this is first excited state. The value of energy people in harmonic oscillator is n plus half h squared omega. But here remember n starts from 0. In boxes it starts from 1, but in harmonic oscillator it starts from 0. So for ground state n is 0. For first excited state n is 1. So here the energy E1, okay, whatever you want to write, E1 energy people, that is actually 0 plus 1 h squared omega. Okay. Energy E1 corresponding to psi1, it's 0 plus 1 h squared omega people. You can write EP if you want, if n becomes confusing by any chance. Okay, whatever. Don't write anything there. Okay. So energy, just general energy, whatever people write it. Even here is 0 plus half h squared omega. It's not 1 plus half. because I have made it complicated by not giving nth excited state. I hope you remember yesterday I told you En was nth excited state, but I have mentioned that it's not nth excited, it's nth level this time. Okay? So for first level, N is 0. So energy of the first level is 0 here. Okay, 0 plus half h squared omega, which is half h squared omega. Similarly, energy of the second level is 1 plus half h squared omega. I hope you understood this. Please tell me if not. Okay, you can make M.
Please repeat.
Sure, and I will suggest you to make it M this time, because this time N and M are not equal. No? Okay, so the thing is, yesterday, what did we learn yesterday? Yesterday we learned whatever was the psi n, respective n was nth excited state. Okay, and for any excited state, the value was direct. It was n plus half h squared omega. So for ground state, it means 0 excited state. No excitation at the ground state. It's 0 plus half h squared omega. Then E1 was 1 plus half h squared omega, because first excited state. Okay, E2 is 2 plus half h squared omega. E3 is 3 plus half h squared omega, because that was direct. But today I am not giving this. In the problem, I have purposely complicated that it's nth level this time, psi n. So when you say psi 1, it's first level, psi 2 is second level. First level means ground state, second level means first excited state. Ground state has n equals to 0, first excited has n equals to 1. So instead of writing n, I am using the letter m. So that again there is no confusion with it. So instead of writing n plus half h squared omega, I'm writing m plus half h squared omega purposely. Okay. So anyway, so energy of E1 will be 0 plus half h squared omega, and energy of E2, energy of the second level will be 1 plus half h squared omega. Clear now?
सर यहाँ m एक्साइटेड स्टेट तो है
नहीं ना, नहीं है. That's what I'm saying. It's not.
सर फर्स्ट लेवल में 0 एक्साइटेड स्टेट तो m इक्वल टू 0 रखेंगे ना E1 के लिए
हाँ 0 रखेंगे, but it's 0 excited state. M is not the problem. Problem is n. इसलिए I made it n. If you would have written it n, what would have happened? E1 would be 1 ना, वो mistake हो जाता ना. Is E1 1? ना, E1 is 0. Understood? And hence I made it m so that the confusion is avoided. Okay, because psi 1 is not 1. That's what I'm saying people this time. This time psi 2 does not have two values. It's time. Yesterday E0 had 0, E1 had 1, E2 had 2. Directly, like directly end up writing it. Okay, because it was excited state here. But now I just made a small change. I hope it's understood. If not,
yes sir understood
okay, so there's a comment here. Sir, student can share doubts. Picture on identical number. We will share this doubts on your number with student's name. Sir. Okay. So see, there is an option. If you have doubts, you can send it to this number. They have mentioned 9950340570. This is identical helpline number, or whatever you call it. So like class support number. So just mail them your doubts here and tell them that you forward this to them. So they will share it to me along with your name that was asked this doubt. So this is also a method, or anyway you have my email address, that also can be done. But this is a more better method, convenient. WhatsApp direct. Okay. So you send them, they will forward me, and then I will send them and they will forward you whatever you want.
So WhatsApp or mail to this number?
This is a mobile number. How will you get it? You do whatever you want to do. You have a choice.
If there is no WhatsApp in that number, so you cannot WhatsApp. So that is
There has to be a WhatsApp here. I think so. So, Imran sir, do we have a WhatsApp on this? WhatsApp is available. Yes, it's available. Okay.
sir. Okay.
Okay.
yes sir yes.
Okay, people. Arun, understood? Arash, who asked this?
Yes, sir.
Okay. Chalo, shall we? Let me explain.
yes sir
Okay. So let's complete this now. So our answer, people, is ready. So the energy was half into E1 plus half into E2. That's it. No? Probability of E1 into E1, probability of E2 into E2. Both the probabilities were half. But this time, this is actually half h squared omega. It's not 3 by 2 h squared omega. And this one is 3 by 2 h squared omega. Half and 3 by 2. So the answer is 1 by 4 h squared omega plus 3 by 4 h squared omega. That's 4 by 4 h squared omega. Answer is just h squared omega. I hope you understood this. Tell me if not. So yesterday E0 was half h squared omega, people, and E1 was 3 by 2 h squared omega. That's the difference. So you have to take care of what language they are using first. And also you need to remember how n starts. For boxes, n starts from 1 for boxes. It starts from 1, but for harmonic oscillator, it starts from 0. A lot of trickiness that we go into this, even though the questions are easy actually, but it's all about little tricks. Okay, people, please ask if you have any questions. So that is done, and we have already taken all the questions related to Fermions, bosons, spinors, formulas. So now let's learn anisotropic harmonic oscillator. A couple of questions on that. Anisotropic harmonic oscillator. So anisotropic exists only in 2D and 3D. 1D does not have anisotropic because 1D has only one frequency. Okay, so when you say anisotropic, there is only 2D anisotropic. Okay, and you can write 2D anisotropic harmonic oscillator, and similarly you have a 3D anisotropic harmonic oscillator. So I'll directly take a question so that you understand on the basis of the question only. Okay, so suppose they have given us potential V of an anisotropic harmonic oscillator, which is half m omega square into 4x square plus 9y square. So what is the meaning of anisotropic, by the way? That the angular frequencies won't be equal this time. Omega x won't be equal to omega y, and here also omega x won't be equal to omega y, won't be equal to omega z. I mean, here two of them can be equal, but all the three cannot be equal. Out of the three, suppose these two are equal, it's fine in that case. But all the three together simultaneously cannot be equal. Otherwise, it becomes isotropic automatically. Okay, but don't write it now. Just write it. Just write omega x, omega y. They may be equal, they may not be equal. We don't care. Okay, and here also we don't care if they are equal or not, because it's anyway general case. Anisotropic is a general case. Isotropic is a special case. Okay, so they may be equal, may not be equal, they may be equal, may not be equal, whatever. So V of x is given to us, and they're asking us, fine. Let me check.
सर ax square y square है ना
No, 4x square 9y square. 4x square 9y square.
okay sir
And
It's the potential of what?
2D harmonic oscillator. 2D anisotropic harmonic oscillator. X and Y is given, no? So it should be understood, right? So 2D anisotropic harmonic oscillator. Just a second. So they are asking us find energy corresponding to state. Corresponding to okay, so ground state. Ground state. Suppose so side this is harmonic oscillator 0 0. Let's give it 0 0. Okay. That's the question right now. Okay. So first of all, I hope you remember that when you talk about potential people, it is actually half kx square in 1D. Okay, k is actually m omega square, and then you have x square. Okay, but when you talk about 2D, x comma y, so you have what? Half m omega square x square plus half m omega square y square. And you have dx and dy both actually this time. Now this time it's sum of dx plus dy both actually. Okay, but who told you that omega x and omega y will be equal? They are equal only in isotropic cases. Otherwise, they may or may not be equal. So this is the concept we need to use here. So what is the potential they have given us? They have given us potential. Let's expand this. Okay, half m omega square 4x square, half m omega square 4x square plus half m omega square 9y square. Okay, so can we find omega x and omega y by simply comparing these? I can. What is omega x? 4x, 4 omega square. Okay. So this that's omega x square. Okay. So from this we understand omega x will be 2 omega. And similarly, what is omega y square? 9 omega square. Okay. So that's it. Omega y is 3 omega b. We found out omega x omega y. Now we already know how to find energy. N plus half x squared omega x, n plus half x squared omega y. That's it. It's not difficult. It's simple. Okay. But provided students have learned this. Make it okay. So this time we will not use n plus 1 x squared omega. If you remember, for isotopic people in 2D, answer was just n plus 1 x squared omega. N is x plus ny. In 3D it was n plus 3 by 2 x squared omega. In 1D it was n plus half x squared omega. In 2D it was n plus 1 x squared omega. In 3D it was n plus 3 by 2 x squared omega. But we are not going to use any of them. We will just say n plus half x squared omega plus n plus half x squared omega. What is omega x? What is omega y? Okay. Copy this. Let me go to the next page then. I hope you are with me.
So please back to the last page once.
Sure.
So in the question, please put omega x and omega y.
No. There is no omega x omega. There is only omega. Now
So
you
like,
expand.
how can I?
It's we have that's what now omega is given to you. Now if you expand this, see if you expand, you have got omega square into 4, na? You have got omega square into 9. So if you compare
Okay.
this and this, so omega x square is 4 omega square, no? And omega y square is 9 omega square. So you have got omega x is 2 omega and omega y is 3 omega.
Okay.
Okay, it's omega only here. Okay, so done people. Please tell me if you have any confusion. Don't hesitate.
एनर्जी यहाँ 2 बार निकालना पड़ेगा along x and y.
And directly but we will write, no? We will directly write nx and y. So they're asking us to find it corresponding to 0, 0 by the way. They have mentioned. But anyway, so energy, if you remember, you can directly write enx plus en y. It's scalar. So enx plus en y. Okay. So you can directly say it's nx plus half h squared omega plus ny plus half h squared omega. But the difference is last time omega was same. Now it won't be same. One is omega x, another is omega y. And we have found out omega x, omega y now. That's it. So what do we have? Nx is basically 0. We have limits. Nx and y 0. Okay. So 0 plus half. So we just have half h squared omega x. 0 plus half. We have got half h squared omega y. So the answer is half into h squared. What is omega x? Omega x is 2 omega. Correct. Plus half into h squared into what is omega y? Omega y is 3 omega. So the answer becomes 2 gets cancelled, h squared omega plus 3 by 2 h squared omega. Your answer is 5 by 2 h squared omega. Understood, everyone. Ground state of this is 5 by 2 h squared omega. People, ground state of 2D was just h squared omega, remember. Of 1D it was 1 h squared omega, half h squared omega. Of 2D it was just h squared omega, and of 3D it was h 3 by 2 h squared omega. So this would have been the answer in a 2D isotopic. But now the ground state in 2D anisotropic, the given isotopic is 5 by 2 h squared omega. Is that clear, people?
Yes, sir, very much.
Good. Okay. Sure. Now we can start the next topic. Oh no, wait, I will give you another question on this. You can try. Let's take another question. Because I have this feeling that they must ask a question on anisotropic here. The reason is only that now everybody knows that the questions on bosons, fermions, spins, and fermions are expected, like 1D box, 2D box. So they have to increase some level in that. Okay, so let's see and hope that they ask this question. Because not many would have prepared anisotropic. So suppose I'm giving you a potential. Let me randomly think of something. In 3D, I'll give you, and you can try. Okay, I'm thinking 0.5 m omega square plus 2 m omega square x square, if you are okay, m omega square x square plus 2 m omega square y square plus 4.5 m omega square z square. I need you to find energy corresponding to let's say triple two state. What is triple two state? Which state is this? That's a read whatever. They have to give us this thing. Energy corresponding to triple two state. Please find. Take it. First, can you tell me omega x, omega y, omega z respectively?
Omega x, omega, omega y 2 omega, omega z 3 omega.
Okay. After this, it's time pass. Let's hope they ask anisotropic. मजा आएगा. Because I've not done that before, so it will be great. Okay, so you just have to compare this with half m omega x square. Okay, omega x square you write, and half m omega square y square. This is omega y square basically, and then you have half m omega z square, half m omega square x square, y square, and z square respectively. So m omega m square you can basically ignore. 0.5 omega square is half omega x square. 0.5.
15 h omega.
Maybe, I don't know, I created it randomly. So 0.5 omega square, this is half omega x square. Just compare these two. Or directly write. If you're not comfortable, people, you can directly write half m omega square x square. This is equal to 0.5 m omega x square. Just compare the whole term. If you wanted that, you can also do that. Because things anyway will get cancelled. Omega gets cancelled, x square gets cancelled, 0.5 half gets cancelled. So you get that omega square is omega x square. It means omega and omega x are the same stuff here. Okay. Very similarly, you can compare these two directly. So if you compare, again, what will happen? M and M will get cancelled, y square will get cancelled. 2 omega square will be equal to half omega y square. So 4 omega square will be omega y square. But I can say 2 omega will be omega y. That's also done. Omega y is 2 omega. Okay. And similarly, here also if you compare M gets cancelled, z square gets cancelled, you will have 4.5 omega square. Okay. This is omega z square by 2. So you have 9 omega square is omega z square. You have 3 omega is omega z. Direct also you can compare, no problem. So omega x is omega, omega y is 2 omega, omega z is 3 omega. Done, people?
Yes, sir.
Yes. So after this unit, I write energy of 2 to 2. So energy is basically nx plus half h squared omega x plus ny plus half h squared omega y, and then nz plus half h squared omega z. Okay. So this will be equal to nx, ny, nz, all of them are 2. So 2 plus 1 by 2 is 5 by 2. So 5 by 2 h squared omega x plus 5 by 2 h squared omega y plus 5 by 2 h squared omega z. Okay. So I can take 5 by 2 h squared common. I'm left with omega x plus omega y plus omega z. So the answer is 5 by 2 h squared into. omega plus 2 omega plus 3 omega, which is 6 omega people. So 2 ones are 2 3s are absolutely answer is 15 asteroid omega. Chalo, great. So we complete harmonic oscillators here too. Nice. And now we'll start with all the different kind of potentials we want to learn. Okay. See people, on the very first lecture of this chapter, when we started with applications of Schrodinger equation, I had taken a free particle problem first. After completing the free particle, we took 1D box ka whole complete derivation. 1D box ka complete derivation. Okay. And after 1D box, we directly wrote 2D, we directly wrote 3D, we directly wrote harmonic, 1, 2, 3, all of them. Very similarly, now I will take one complete derivation on step potential when I will try to explain everything. And for the others, we will just create the equation, we'll just create the differential equations and then skip the steps. Okay. After this, basically is differential equation solving mathematics. But for now, we will take one derivation completely. That's the step potential. Okay. I hope you have copied this. Let's start with the next section of this chapter, people. Please give heading step potential. And all the concepts that you will learn in this, listen. So there are many kinds of potential, okay? Like standard potentials that we talk about. So 1D box is an infinite potential. Free particle is basically where potential is zero. Step potential we are taking. Then there is symmetric potential, barrier potential. So different kinds of potential systems we can always have. Square well potential, rectangular potential, whatever. However, in exam, it's not necessary they will take any of the standard potentials. They create their own potentials time and again. For example, in the recently done TIFR paper, I think I saw a question there where they had done some potential like this probably. Okay, so it's kind of a finite potential, symmetric potential, but usually students have done a finite symmetric potential like this actually. But they had done some shift of origin with this. Probably something like this was there. I don't remember. So I have the whole question paper that student. You have got your responses. Huh? So one student had forwarded me his response. So from in that I had seen this some kind of question. So the point is how to crack those questions will basically lie in the theory that we are going to develop in this problem. Okay, so this problem will only teach you how do we crack any kind of potential problem. So we'll take it very slow. We'll invest our complete hour in learning step potential. Okay, so let's get started. First of all, the word step means staircase. Like literally somebody's taking a staircase for a step. So this is nothing but step potential itself. Okay. So how it looks like, let's say we have a v of x and let's say there is x. This is x axis, there is v of x axis, negative x axis. Okay. So a popular step potential is something like where you have a v of x is 0 b. Okay, initially on the left side. And all of a sudden there is a jump. All of a sudden there is a jump. Okay. And then it becomes constant. So it's like a ceiling, people, a staircase that you're climbing. You're taking a step. That's it. So now you have got some constant potential, let's say v0. Let's say this value is v0. And here the value is 0, absolutely. Okay. So how can you write this potential? I can say v of x is basically the value is 0 when for x less than 0, and the value is v0 where for x greater than 0. Okay. First to copy this. This is the step potential. You can write equality, but the point is it has logically speaking it should be discontinuous, no? Because you cannot have a sudden jump. Okay, it's a sudden jump, basically. So that has to be discontinuous, and hence I'm not using equality. So there's a sudden jump. Equality would mean that it has two values at the same point. It would be a bit absurd. So we don't write equality. But the wave function will be continuous. I had taught you this in the theorem. We don't care whether the potential is continuous or not, but the wave function will be continuous. That we have learned if you remember. It was one of the theorems only. Okay. So we don't care whether
it should be finite only.
Wave function will be finite and it will be continuous.
No, potential should be finite, no? Only then wave function.
Yes, absolutely. Perfect. Yes. So is this finite? 0 is finite, right? And this is also finite. So as far as the potential is finite, we don't care whether it's continuous or discontinuous. That was the statement. So as far as it's finite, wave function will be finite, it will be continuous, and at the same time, derivative of the wave function will also be continuous. That was the definition of well-behaved wave function. Okay. But anyway, so the point is the wave function will also exist. We don't know the value, but wave function will exist. It will have some value. It will have some value for x less than 0, and it will have some value for x greater than 0. Okay. So we don't know the value yet. But wave function will be continuous. So here you can apply equality. As far as potential is finite, people, wave function will be continuous. Its derivative will also be continuous. The important is that v of x should be finite. I'll write it again if you want. As far as v of x is finite. We don't care whether it's continuous or discontinuous. As far as it's finite, wave function will be continuous, and its derivative will also be continuous. Okay. Psi of x and d psi by dx, both of them will be continuous. So here you can write equality. We don't know the value. We have to find the value. So that is one of the kind of questions for 1 mark that they ask. They will give you a random step potential. They'll ask you what is the wave function in region 1 and what is the wave function in region 2. Let's call this region 1. People, let's call this region 2. Okay. Sure. Next, let's write our this. What do we say? Schrodinger equation. People. Okay. So what is our Schrodinger equation? Now I'm writing the second Schrodinger equation directly, as in the one after small adjustment. It was, if you remember, d square psi upon dx square plus 2m upon x square into e minus b into psi. This is 0. I'm jumping to this result directly now. Oh, that's fine. Next. Now there are two cases. What is E, by the way? E is the energy of the particle. Okay, the incident particle. So right now we don't know whether the incident particle will have a lesser energy or whether the incident particle will have a greater energy than V0. So step potential has two cases: E greater than V0, E less than V0. Today we are completely working on only one case, that is greater than V0 case. Tomorrow we'll take the lesser V0. Okay. So let's say we have a wave function, a particle coming from left side. It has energy E, which is greater than V0. That's the case we are taking. Draw this. Case 1 we are taking. Okay.
So can you please repeat? I was out of the meeting.
Sure. So all that. We did is first of all, I just wrote Schrodinger equation, that is. And secondly, we don't know whether this value of E will be, it will be less than the step potential or whether it will be greater than step potential. So there are two cases in step potential. One where incident energy is greater, other is where incident energy is lesser. So today's lecture is completely on the greater case. Tomorrow we'll take the lesser case. Okay. So let's say you have got a particle incident from region 1 entering to region 2, and it has got energy E, which is greater than V0. At this right now.
Our aim is to find the wave function, or what is
everything, not only wave. After wave function, we'll be learning probability density, current density, reflection coefficient, transmission coefficient. So from one step potential, anything and everything that could be asked is what I'm going to take this. Okay.
Yes.
Okay. So first we have noted that. That's fine. So let's start with the case. So first let's discuss region 1. So people, what is the value of V in region 1? Value of V in region 1 is 0. So what will be our Schrodinger equation? D square psi upon dx square plus 2m upon x square into e minus 0 into psi. This is 0. So we will have d square psi upon dx square plus 2me upon x square into psi. This is 0. We can do one thing. We can immediately call it psi 1 because we're talking about region 1 now. So let's call it psi 1 best. I'm purposely writing psi 1. Next.
This is on the left of left graph, right?
This on the left graph, region 1 completely where potential is 0. Okay. Then after this we do let people. You know what is the let part? We say this is k square. So we will say let us say this 2me upon x square. Let's say this is k square. Or write it k1 square this time. Write it k1 square. Because later we will also have k2 square for RHS now, and that will be different. So our equation becomes d square psi 1 upon dx square plus k1 square psi 1. This is 0. K is propagation constant only. It's not a random k, that also I've already explained. Then we go next.
Alright, so
Okay.
what is this one psi 1? What?
Because it's region 1.
So the
function
wave,
region 1.
wave function region. Okay.
Because that will change when we enter region 2. No, potential is different. So k will change, and lambda will change, and the wave function will change. Okay. So region 2 wave function will be different. And we wrote it here, no? Wave function will be different at psi naught, like less than 0 and greater than 0. So if you want to connect psi 1 here, we don't know the value of psi 1. And connect psi 2 here, we don't know the value of psi 2. We want to find that.
Yes, sir.
Chalo. Just let me remember this, okay? So we have d square psi 1 plus k1 square psi 1. This is 0. I've written d square 1, d square is capital D square. That you already know. So d square plus k1 square into psi 1, that is 0. Wave function cannot be 0 unless the potential is infinite when you take analysis. I will say that d square plus k1 square, this has to be 0. So d square will be minus k1 square. So d square will be, so d will be plus or minus under root of minus k1 square. So d will be plus or minus, I can write under root minus 1 into under root k. So this is d is plus or minus k square. Under root minus 1 is I, under root k square is k. So we have got a complex pair. Okay, we have got a complex pair. And I've already made you write again at the beginning of this chapter. People, what happens when we have a different combinations? We have written for real equals, we have written for real unequals, and we have written for complex pair also. Okay, so I can compare this with alpha plus or minus beta I. Okay, so alpha is 0 and beta is k. So what is the wave function? People? The wave
C1 cos
function
plus C2 sin
k x. Okay, so psi 1 is actually equal e raised to alpha x into c1 cos beta x plus c2 sin beta x. Whenever we have complex pair, this is what I have asked you to remember. Okay, that's it. So psi 1 would be e raised to alpha, that's 0, c1 cos kx plus c2 sin kx. Okay, so anything raised to 0, that's 1. So psi 1 we have found out it's c1 cos kx plus c2 sin kx.
K1 होगा.
sir K1
It's
K1
everywhere, absolutely. K1, here also it's K1. Here also it's K1x, C1 cos K1x, C2 sin K1x. We are writing K1 because on right reason the value of K will change, and hence we will then write K2. Let's say we could have directly written this had we been in touch with the first lecture's idea. Whenever the potential is 0, if you remember, wave function is always this.
yes sir
We could have directly jumped on this conclusion.
Sir, directly jump हुए थे कॉपी में दो भी directly लिखा है.
Directly, सही है. Good. C1 cos K1x plus C2 sin K1x. However, the thing is, now I'm not going to use this thing. Do you remember I had when I made you write real, equal, real, unequal, and complex pair? I asked you to leave some space.
yes sir वही मैं पूछने वाली थी एकदम आपने 3-4 लाइन छोड़ने के लिए कहा
Yes. So now we have to fill that space, people. Go back to that page. So for complex pair, there is another thing that we can use. Okay. Go back to that page, people. Where you have written complex pair, and you have written whatever I think you wrote. I think you wrote y, and you had written e raised to alpha x and c1 cos beta x plus c2 sin beta x. Okay. And then I had asked you to leave 3-4 lines here. Okay. Go back to that page. Beginning of this chapter, people.
yes sir yes मैंने
Found it, everyone? Take your time. Go back to that page. So I do everything for a reason, okay? Next. So what is that other wave function which we can use? Okay, the other one is C1. Or actually, you know, I so want to tell you the whole story of it, but the time is a constraint. The thing is, don't write it first of all. I just want to explain something. So I had always by hearted during my preparation times that the other wave function is basically C1 e raised to I m1x. Okay, C1 e raised to I m1x plus C2 e raised to I m2x. This is the other wave function. That is what I had by hearted. Okay, but only basically since when I started teaching and I had to teach this. So obviously students would ask and come up with a question that, sir, why does this other wave function exist or whatever. But the problem was, you know, M1 is the basically determinant people where you write alpha plus beta x, alpha plus beta I, and M2 is alpha minus beta I. Basically, M2 is alpha minus beta I. So if you substitute it here, if you use Euler's theorem, the numerator, these two were, were not matching actually when I applied Euler's theorem, because e raised to I think cos theta plus I sin theta, they were not matching. But then I thought, what if this, what I had learned is a partial thing, and that is what came out to be two people. The correct answer is actually e raised to alpha x into c1 cos I beta x, not cos, sorry, c1 e raised to I beta x plus c2 e raised to minus I beta x. This is the correct answer. Achha, by the way, एक और thing, this c1 and this c1 are not same, and this c2 and this c2 are not. They are arbitrary constants. So if you want to connect a1 and a2, doesn't matter. These two are just arbitrary constants, are not necessarily equal. Okay, write this, and then I'll explain why this is. First, write this. Okay, so this is the second one, the second formula. And the thing that I was saying, that I had only thought answer is only this. The thing is, people, the books have used the fact that alpha is 0. If alpha is 0, then anything raised to 0 becomes 1, and hence, you know, they never write RHS. They directly write this. They tell that any book, check it directly, any book, they will directly write a region 1 has wave function this. No explanation given whatsoever. Okay, the only reason it becomes is because alpha is 0 and anything raised to 0 becomes 1 people actually. Okay, I cannot do control Z exactly now. So I'll just rewrite. So anyway, the second formula that I wanted you to write is e raised to alpha x, and that is some random constant a1 which is not connected to c1. Okay, e raised to I m1x plus a2 e raised to minus I m2x. M1, not M1, it was beta. I beta x plus e raised to minus I beta x. Now, only to feed your curiosity, people, why this is correct, we can immediately learn the reverse engineering process. Okay, I'm going to go from here to here. So let's write this term first. Take alpha e raised to alpha x inside. What will you get? E raised to alpha x plus I beta x, correct? Plus what you will get here? E raised to alpha x minus I beta x, correct? I'm just taking e raised to alpha x inside, people. X raised to a into x raised to b. X raised to a plus b ना यार. X raised to a into x raised to b. So that's x raised to
सर A2 कहाँ गया?
अच्छा A2 तो है ना? कौन बोल रहा है? देखो देखो देखो
Yes, sir.
A2 is also there, people. Okay. Next, so this is a1 e raised to. Now, we can do one thing here. Hang on, I'm still thinking.
सर अल्फा अंदर नहीं लेना था.
नहीं लेंगे, मैं वही सोच रहा हूँ because Euler's theorem directly I can apply. Let's apply Euler's theorem, people. What is e raised to I theta?
Cos theta plus I
I sin theta. So e raised to I beta x. So that is basically cos beta x plus I sin beta x. Okay. Again, what is e raised to minus I theta?
cos beta x minus I sin beta x.
Yes, cos beta x minus I sin beta x. Okay. So this becomes cos beta x minus I sin beta x. Okay. A to B. Any questions until you ask? I'll just apply Euler's theorem and I want you to understand why this is correct and why these two are connected. Okay. Now expand. So what do we have? E raised to alpha x. Expand this. You have got a1 cos beta x plus a1 I sin beta x plus a2 cos beta x plus minus a2 I sin beta x. People, just take cos terms together and just take sin terms together. What do you have? E raised to alpha x into. If you take cos terms together, okay, what do you have? A1 plus a2 into cos beta x. Okay, and just take sin terms together. So what do we have? A1 I minus a2 I. You know, A1 I minus a2 I. This is sin beta x. Do you remember that our constants are allowed to be complex?
Yes, sir.
So this is constant C1 and this is constant C2. E raised to alpha C1 cos beta x plus C2 sin beta x.
तो सर A1 plus A2 ये इक्वल होगा ना
Yes,
C1
A1 plus A2 is C1 and A1 I minus A2 I is C2 actually. ठीक है?
Okay, sir.
चलो, make a note. And nobody taught me this. This is just self-learning. You know, I recently saw a meme. Like there are things which people teach, but it's unnecessary. For example, there was a story where somebody had put that it's winter right now. What is the most irritating part in this winter? If you're wearing a full sleeve, full sleeve shirt, people, if you're wearing a full sleeve shirt, and at the same time, if suppose you want to wear a jacket, what's the most problematic part? When you wear the jacket, the shirt goes up. Huh?
Yes, sir.
That's the most irritating part. Shirt is already full. Plus, you're putting your hand inside the shirt goes up. That's the most irritating part. So how do we save ourselves from this? So
Sir, shirt को पकड़ के.
So they were teaching this. You should hold your shirt like this, and then you should wear. This is self-learning. People learn this by themselves. Okay, but okay, it was nice. But the point is, there are things which people don't teach you. You can just learn them by yourselves. So this is one of the things, and I feel good about it. Okay, take a note. Okay.
Yes, sir.
Chalo. Let me know if writing. Okay. So going back to our problem. Okay. So we are not going to use this wave function now. Okay. So in this we have got d is plus or minus I k1 now. Go back, please. D is plus or minus I k1. So what we are going to say, this is 0 plus or minus I k1. So you can say that alpha is 0 and beta is k1. But we will use the formula that the value of psi1 will be equal to e raised to alpha x into c1 e raised to I beta x plus c2 e raised to minus I beta x. So we'll use this formula, people. Okay. So this becomes e raised to 0, c1 e raised to so much is going on in my head right now. I beta x, that's I k1x. Okay. Plus c2 e raised to minus I beta x, that's minus I k1x. Okay. Anything raised to 0 is 1. So I can directly say this is c1 e raised to I k1x plus c2 e raised to I minus I k1x. And people, all the books have written this result directly without any explanation. They're like, we know. We don't know. Yeah, you know that. We don't know that. But okay. Okay. Make a note. Two things in this are very popular. One is let, other is let. But my favorite English word, I have told you that already. Do you remember? Right. Okay. So now the question right now is obviously how to find these constants. For that we have to use boundary conditions. Wave function on the right will be equal to wave function on the left at the boundary, and derivative of the wave function on the left will be equal to derivative of the wave function on the right at the boundary. But for that we need the wave function on the right side. So now let's find it. Let's say this is equation 1. Okay? So now let's work on the second one. I hope you have copied this. Next. Proceeding ahead. Okay. So region 2. Now the value of v of x is v0 and it's constant. Okay. So our Schrodinger equation becomes d square psi 2. I'm writing psi 2 purposely. D square psi upon dx square plus 2m upon x square e minus v people. V is v0 into psi. Psi is psi 2. This is 0. And then we will say let this whole term this time we will say k2. So let k2 square. Okay, let k2 square be 2m upon x square into e minus v0. Okay. People, clearly k1 is greater than k2. K1 is greater than k2 because k1 was just 2m upon x square now, and k2 has a subtraction term. Okay. Next, so what does this further becomes? Proceeding ahead. I hope you have written this. So we have got d square psi 2 plus k2 square psi 2. This is 0. People, the story is similar if you realize you don't have to solve this till the very end. You can directly write the final result. Last time we had k1 square, now I've got k2 square. Even plus is plus. It's not a plus, it's become minus. Just last time I had k1, now we have k2. So I directly write the result. So what should be the value of psi 2? Okay. I will write my favorite word. Okay. Similarly, so psi 2 is don't write c1, c2. C1, c2 you have already used now. So we'll go with c3 and c4. That's the difference. So c3 e raised to I k2 x plus c4 e raised to minus I k2 x. I hope this is fine. That's a matter. Remember in complex it looks like this. In real also it's similar. When you have real and unequal, but there you had the c1 e raised to m1x and c2 e raised to m2x. There you did not have I term. But in complex you have I beta x plus or minus I beta x. So just don't get confused. It is somewhat similar, but it's different. C1 e raised to m1x, c2 e raised to m2x. That was for real and unequal people. And here anyway you have a pair of plus and minus. Okay, next.
Sir, please repeat what are you saying?
Sure. So see in complex when we get complex pair where we write that the value of b is alpha plus or minus beta. Okay, and beta x. Such that if alpha is 0, so it becomes only plus or minus beta x. Okay, if alpha is 0. Okay, I beta x, sorry. So I'm thinking something more in this now. But anyway, I beta x. No, this alpha plus or minus I beta. Okay, what is the solution? How do you write y? Y is e raised to alpha x into c1 e raised to I beta x plus c2 e raised to minus I beta x, correct? So I just wanted to clarify that when you talk about real and unequal pairs, like for example, you end up getting b is 3 is suppose these 3 and minus 4. Real we have and they are unequal also. Okay, so one is m1, other is m2. How do you write the solution there? It is c1 e raised to m1x and c2 e raised to m2. So the only confrontation there was that this and this looks similar, but there is a difference. This is m1 m2. Here it is I beta, this is minus I beta. There is a minus sign to take care of. Okay,
Yes,
because if alpha becomes 0, if alpha becomes 0, then this becomes c1 e raised to I beta x plus c2 e raised to minus I beta x. But this happens when alpha is 0. Okay, and actually they are one and the same thing if you realize. Now these two are one and the same thing, but it happens only when alpha is 0. Why these two are one and the same thing? Because what is the first slope? Plus I beta, and what is the second slope? Minus I beta. Do you realize it, people? The first slope is actually plus I beta, and the second slope is minus I beta. Not slope, the first solution. What is the word I use? Root. First root is plus I beta, and the second root is minus I beta, and alpha is 0. So this is plus I beta x m1x, and m2x is minus I beta x. So actually these two are same thing, but this happens only when alpha is 0. That's what I'm saying.
Yes, sir. Yes, sir. I got it.
But anyway, too much of confusion. We'll just copy this. Others, please ask me if you have any questions until here. Okay, now comes the more important part. So before you start equating them at the boundary and equating the derivatives at the boundary, you have read it in the books. They tell you that this constant has become 0 and that constant has become 0. I tried to explain one idea about it, if you remember, that wave function should be finite. That's what I told you to remember. Do you remember the example that I had given? I think I given something like e raised to, suppose I give you e raised to x. Suppose this is a wave function given to you. But in the question, if it is given, I think this was the example that I had taken. So I was a raised to x, and let's say b raised to minus x. And suppose they have given x is greater than 0. Okay, it means x can take all the values greater than 0. It can take 0.1, 0.2, 0.3, 0.4, 0.5, anything. Let's say greater than or equal to 0. Okay, so if you substitute 0, do we have any problem? Just check. Do we have a problem if you substitute 0? E raised to 0 plus b raised to minus 0, no problem. Anything raised to 0 is 1, and anything raised to 0 is still 1 people. So you're getting a plus b. Substitution is not a problem if you substitute 0. If you substitute 1, we don't have a problem. If you substitute 2, we don't have a problem. We can substitute anything. But people, what will happen if you substitute infinity? Because they have mentioned it's greater than 0. So it can be anything now. If you substitute infinity, then what is the problem?
Infinite हो जाएगा.
It becomes infinite. You are getting e raised to infinite plus b e raised to minus infinite. E raised to minus infinite is not a problem.
0.
E raised to minus infinite is not at all a problem. Okay, because when you see e raised to minus infinite, that's 1 upon e raised to infinite, which is 1 upon infinity, and upon infinity is 0. So this term becomes 0. Wave function becoming 0 is not a problem, people. This term will become 0. But here, this thing is making it infinity. Because this is making it infinity, the important thing is that it cannot exist. Wave function must be finite. And because it cannot exist, you have to see the value of a must be 0. It cannot exist. So what will be your wave function, people? Wave function will be just b e raised to minus ix. We have done this, but we are recalling this. Write it again. It cannot be infinite. Okay? It cannot be infinite. It means this term cannot exist. It cannot exist. I hope you recall this and I hope you understood this.
Yes, sir.
This is just an example. First you copy this and then there is another more layer to this.
Copy, sir.
Others? What is the time here? I don't know if we don't have that. Okay, let's see. Okay, then next. Let me write it, okay? Now, however, this idea that we just used, okay? Okay, first I want to practice more in this. Suppose if I give you x less than or equal to 0, then what will happen? Same question. A raised to x plus b raised to minus x. But given as x is less than or equal to 0, same question.
B हो जाएगा infinite.
So this time, people, it is less than or equal to 0. So it can take 0. 0 is not a problem, you already know. It can be minus 1, minus 2, minus 3, minus 4. That is also not a problem. Problem is when it becomes minus infinity. So when x becomes minus infinity, the thing is minus of minus this function becomes infinite. So this cannot exist. This term cannot exist because it is making the function infinity. So in this case, I is a raised to x. Okay, right, please. In this case, the second term cannot exist. Okay. I hope you are with me. Okay, now, so people, this idea that we learned is valid only when functions are real. If the functions are complex, for example, this function that we have, it's a complex function. It's a complex function. You cannot use this idea of infinity minus infinity. So then, how to identify? Because if you have learned this in your BSc, they still have claimed that that some constant becomes 0, some coefficient becomes 0. But now we cannot use the concept of infinity and minus infinity. We cannot use, basically write it if you know. If the wave function is complex, write it. If the wave function is complex, then we cannot use the concept of finite and infinite. Write it first. If the wave function is complex, then we cannot use the function of if the wave function is complex, then we cannot use the idea of finite and infinite. Basically, this idea we cannot use it. So what to do in that case? Now, if you ask me, that's so why did you convert a cosine into e raised to I? Like, what was the importance? And basically, you should have asked me, so when to use cosine and when to use e raised to I, because both are valid. No? We learned both are valid, but then what was the need for converting it into e raised to I format? The reason is, people, what is equation of a plane wave? In electromagnetism,
A into exponential divided iota kx minus omega t.
Perfect. And tell me one thing, in this when you write I kx minus omega t, what does this tell you? If x is positive, then what is the meaning of it?
Wave
Wave is propagating in positive
x direction.
Good. So here it is telling you wave is propagating in positive x direction. This is the reason, people, because we converted it in this format, a raised to ikx, a raised to minus ikx, c1 raised to ikx, c2 raised to minus ikx, because we can understand the direction of propagation of the wave. So this tells us, about wave is propagating in positive x direction. Write it, please. And now get the beauty. Yes, this is the equation of linear. Okay. Psi. If it was minus, then you write negative x direction. Since it's plus, it's positive x direction. Okay. If here we don't care about omega t, by the way. Plus omega t, minus I don't care about omega t. Okay. All we have to see is plus or minus here. Okay. So we're done. Okay. Let's go back. Now tell me one thing. You already know the directions. Okay. So first of all, on left side, particle is propagating along positive x direction. But if you remember, you have learned this also, that is reflection possible here or not? First of all, is greater than E naught. Classical mechanics prohibits reflection, but I'm sure you have learned that quantum mechanics allow us that there still can be some amount of reflection, even if E is greater than E naught. Write it, please. Write it. Even though E is greater than E naught, even though E is greater than V naught, write it. Even though E is greater than V naught, quantum mechanics allows us that even if E is greater than V naught, quantum mechanics allows us that there could be a possibility that the wave will be reflected back. There could be a possibility. Quantum mechanics allows us that there could be a possibility that the wave function is reflected back. Because classical mechanics prohibits us. Classical mechanics will tell you that reflection coefficient is 0. It cannot be reflected at all. I think I should have made you write a little more neatly. But how much ever I try, I always think that no, it can become more neat and more neat and more neat. But anyway, so what have you written, people? Even if E is greater than V naught, quantum mechanics allows us that the wave can still be reflected back. The wave can still be reflected back. So reflection coefficient, the reflection probability exists, people. Okay, R exists. But remember, classical mechanics prohibits us. Classical mechanics will tell you E is greater than V naught. It has to pass. How can you even tell me that there could be a reflection? E is greater, it has to cross the barrier. So classical mechanics tells us that R should be 0. It cannot be reflected back now because E is greater than V naught. Because E is greater than V naught. Okay. You may have also learned the tunneling idea, the reverse idea. People tell me, if energy is less than V naught, classical will tell you that it can never be transmitted. Here, classical tells you that transmission coefficient must be 0. This is what classical tells you. It cannot be transmitted because E is less than V naught. Sorry, E is less than V naught this time. Okay. But quantum mechanics tell you that a tunneling is possible, and you have learned it probably as quantum tunneling.
Yes, sir, semiconductor में भी होता है.
Yes. So even if energy is less than V naught, there is still a probability that it can still be transmitted to the region. Quantum mechanics will tell us it's not 0. It will still have some value in quantum mechanics. Okay. Write this also. This is for the case E less than V naught. So transmission is
energy of the wave function.
Energy of the wave function. So if energy of the wave function is less than barrier, then logically and classically, people would tell it's less than barrier. It can never cross the barrier. It can never cross V naught. That is classical assumption. Quantum mechanics allows us that there can still be some transmission, and that is known as tunneling effect. Are you with me, people, until here? Even if you have not learned it, I hope you are buying this topic.
Yes, sir.
It's quantum mechanics, so you have to buy it. Okay. But still, any questions, please ask me right now. Because I think there are students from first and second year also in our class, especially those. All good so far? I remember a couple of students who are from first year. I'm not sure if they're in the live class right now. And second year too. Not quite sure. Sunita, I think you are from second year, or Smriti, either of you is from second year BSc. And Arijit was also, I remember, he was also from first or second, but he's not there probably right now.
Sir, I am from final year. I'm also.
Okay. Okay. Chalo, let's continue, people.
I'm also from second year.
Second year, na? Himanshi, okay, right. So people are buying this topic so far?
Yes, sir.
Okay, good. Chalo. So,
99%.
99%. Okay. Okay. Chalo, good. Proceeding ahead. Anyway, so the point is now that going back to this. So people, incidence is possible. It means kx will be positive. Kx will be positive. Like we can have e raised to ikx, correct? Reflection is possible. In quantum mechanics, reflection is possible now. So I can say e raised to minus kx is also allowed. Are you with me? E raised to ikx is allowed. We just learned, people, this plane wave equation. What is the plane wave equation? Ikx means positive direction, and minus ikx means negative direction. Okay. So when you say ikx, that's fine. Ikx is allowed because incident is possible, right? Reason one. And reflection is also possible. So minus ikx is also allowed. It can be reflected back. It can go in the negative x direction. So both of them are allowed. Is this fine so far?
Yes, sir.
Okay. So basically, in the first wave, Psi1, both of them are allowed. Ik is also allowed, and minus ik is also allowed, because this tells you what? This tells you about incident information, and this tells you about reflected information. But remember, quantum mechanics allows reflection. Classically, this will not exist. Classically, this will not exist. Right? Go to Psi1. Go to Psi1. Mention this tells you about incident information. This tells you about reflected information. Okay. Done. Okay. And remember, reflection is possible in quantum. Classically, it shouldn't exist. Okay. Next. But tell me what happens in region 2. Is transmission allowed first of all? In region 2, can we go in this direction? It can. It's greater than what it can. But by any chance, we predict wave traveling in this direction?
No, sir. No, sir.
This is not even possible. Like, how can a wave travel in this direction in the region 2? It means here e raised to ikx is allowed, but you can never have somebody like e raised to minus ikx here. So which term becomes a 0?
C4.
Please write it. Please write it. Please write
सर
it.
ऐसा तो आज तक नहीं पढ़ा सर.
Yes. Okay, happy to know that. Make a note, please. Because I myself, I'm not being taught these things. So anyway, please write it. Okay.
सर इसका डायग्राम देख के ही डर लगता था पहले.
After diagram देखिए और में ऐसा बनने नहीं होता है.
Yes, sir.
Anyway, please write it. E raised to ikx that will exist, and e raised to minus ikx that becomes 0, people. Okay. The reason is where is psi2? This tells us about transmission, which is heavily possible, but this doesn't make sense. Okay. This doesn't even make sense. In reason 2, we cannot even imagine particle traveling in this direction. Okay. So this term C4 has to become 0. So remember, you will use the idea of infinity and minus infinity for real functions. And the reason now I would realize that why did we convert that, e raised to alpha x c1 cos beta x plus c2 sin beta x in this ik format, so that it becomes a plane wave equation which gives us information about the transmission and incidence and reflection. Great. So this is the major part that I wanted to cover. Now let me think, what should I do? Because I cannot complete the whole derivation in the next 10 minutes. But okay. I hope you copied this much.
Yes, sir.
Okay. Okay, so I think we can
Go to Psi1 also. Go to Psi1 also.
Sure. Yes.
Done, sir.
Okay, good. So next. Proceeding ahead. And here we have. So we can simply say that the incident wave function is c1 e raised to I k1x. The reflected, this is not reason 1. I mean incident. So I will write it small, right? Better. Incident wave function is just c1 e raised to I k1x. Reflected wave function is c2 e raised to minus I k1x, and transmission wave function is c3 e raised to I k2x. Okay. Wave function in region 1 is actually sum of incidence and reflection. Sum of these two. And wave function in region 2, it is just transmission. Just transmission. Remember, psi r exists only due to quantum mechanics. It cannot exist in classical. Okay. And now we can find relationship between constants using boundary conditions. Okay. So psi 1 is basically, I can say C1 e raised to I k1x plus C2 e raised to minus I k1x, and psi 2 is just C3 e raised to, which is psi t, it is just C3 e raised to I k2x. Tell me if you have any questions. Proceeding ahead. So let's find relationship between the constants, people. So this is the first partition, like I said. One of the popular questions in JAM is they'll give you first of all separation, and they'll ask you identify the wave functions. So you have to find the wave function in region 1, wave function in region 2. And then obviously you also have to find this term becomes 0. So one major part. Now you can actually not do this. You can actually apply your own head and do this whole thing. If, no matter whatever equation I give. You need a bit more practice, however, but still you have got the gist of how to get psi 1 and psi 2. And even if you have psi 3, psi 4, whatever, you can do this. All you need to solve is differential equation. After differential equation, you have to see real hai, unequal hai, equal hai, and then you have to see whether it's complex or not. If it's real, you will use the idea of infinity and minus infinity, and if it's complex, then we'll use the idea of this plane wave propagation, because incident reflection. So next. Now let's find relationship. So we can use boundary conditions because we know wave function will be continuous. Wave function is continuous at the boundary. Where is boundary, by the way? In the diagram?
At 0.
At 0. Okay. X equals to 0. So that's it. So I can say the value of psi 1 at x equals to 0. It has to be equal to value of psi 2 at x equals to 0, because wave function must be continuous. Okay. So let's substitute, people. Okay. What do we have? C1 e raised to 0. Okay. Plus C2 e raised to minus 0. This is C3 e raised to 0. Okay. So we have got C1 plus C2 is C3. One of the relationships. Even this could be one of the options where they're also asking you which of the following options are correct. It could be an MSQ, and one could be relationship between the constants, 2 people. Okay. And how can we get another equation that we can use derivatives for? Derivatives should also be continuous. Right. Next. Okay. I hope you copied this. Derivative of the wave function d psi by dx should also be continuous. Is also continuous. F x equals to 0. Okay, so we need derivative. So let's first calculate psi 1. Psi 1 was C1 e raised to I k1x plus C2 e raised to minus I k1x. Let's calculate its derivative. So this will be C1 derivative of e raised to x is e raised to x, derivative of e raised to I k1x is e raised to I k1x. Again, you have to redifferentiate this. If you redifferentiate this, you get I k1 additional term. Similarly, derivative of e raised to minus I k1x, that will be e raised to minus I k1x. We have to redifferentiate this. If we redifferentiate this, we get minus I k1. So we have got basically I k1 C1 e raised to I k1x minus I k1 C2 e raised to minus I k1x. And what is the value of this at x equals to 0? Let's write that. So at x equals to 0, the value of this would be equal to, I'll use different color. Okay. I k1 C1 e raised to 0 minus I k1 C2 e raised to 0. Or you can say you have got I k1 C1 minus I k1 C2. You can take I k1 common. So you have got I k1 common C1 minus C2. I will realize basically you're going to have two pairs, C1 plus C1, C1 minus C2. You can solve them, express one constant in terms of another constant, that type of later. Okay.
ठीक है.
Okay.
So please show the previous slide.
Sure. Tell me if you have any questions. I've just substituted the values now. Here, e raised to C1 e raised to 0, C2 e raised to 0, and C3 e raised to 0. Done?
Yes, sir.
Okay. Others also recommend you writing this now. Next, what is psi 2? Psi 2 is C3 e raised to I k2x. So derivative of psi 2 with respect to x. This is C3 e raised to I k2x. Derivative of e raised to x is e raised to x. We will redifferentiate this. We will have I k2 people. So we have got I k2 C3 e raised to I k2x. Again, the value of this at x equals to 0. The value would become I k2 C3, anything raised to 0. That's again 1. We have got I k2 C3. So again, we can apply boundary conditions, but this time we will say derivative of the wave function in region 1, it has to be equal to the derivative of the wave function in region 2. But that happens at the boundary. So we have got C1 plus C2, sorry, C1 minus C2, and what was it? I k1 common. I k1 common, C1 minus C2, we have got I k2 common, C3. Okay. So I and I get cancelled. We have got C1 minus C2 is k2 upon k1 of C3. We have got two equations, people. Okay. There is a background noise. Unmuted.
Done, sir.
Others, let me writing. Done, shall we? Okay. Next. So basically what we have found out is two equations. C1 plus C2 was just C3, and C1 minus C2, it is K2 upon K1 of C3. Okay. Now the question is whom we should express in terms of what? Right? Equation 2, 3, 4, whatever numbers you have given. So suppose 3, 4, doesn't matter. What is C1, C2, C3 matter? What is the importance of it? Can you tell me?
The coefficient of transmission.
No, not coefficient, not coefficient. No, not coefficient. It's amplitude of the plane waves, no? What was psi 1 people? Psi incident. Psi incident was C1 e raised to I k1x. So this is amplitude, no? Amplitude of incident wave. That is the importance of the constant people here. Okay. Similarly, when you wrote psi r, the reflected, it was C2 e raised to I minus I k1x. Okay. So this is amplitude of reflected wave people. Amplitude of reflected wave. And then when you write psi t, which was C3 e raised to I k2x, this is amplitude of transmitted wave people. Amplitude of transmitted wave. Okay. And again, I can explain something very beautiful here. So people, when you talk about reflection coefficients or transmission coefficient or absorption coefficient, people we have learned coefficient, absorption coefficient, reflection coefficient, transmission coefficient. What was that? Basically, it was ratio of what to what? Energy to energy. Like you have learned absorption coefficient was energy absorbed upon energy incident. Correct? Then we had learned reflection coefficient was energy absorbed upon energy incident. But we don't like can I write instead of energy intensity also? Because energy is actually intensity per unit area per unit time. So you can divide area and time. No? That's also fine. So can I say that absorption coefficient, when you have learned that it was actually absorbed energy upon incident energy, I can simply say it's also let's write it I. Okay? You can say it's intensity of absorption upon intensity of incidence, okay? And reflection coefficient, which was reflected energy upon incident energy. Huh? So can I say it's also in reflected intensity upon incident intensity? Are you with me? Anil? Copy this, please.
Yes, sir.
Copy this. So in quantum mechanics, what we do is we use capital coefficients, the capital A, capital A, capital A. No logical reason, we can use smaller. I've just replaced energy with intensity because intensity is energy per unit area per unit time also, so that's fine. Okay. However, I hope you have copied this up. Next. Okay, so our absorption coefficient, I don't care which are the two coefficients that we care about here. So we are assuming no absorption is there. It's not material, it's a boundary by the way. So there is no absorption happening. So in quantum mechanics, we have got reflection and transmission. So can I simply say intensity of reflected upon intensity of incident and intensity of transmission upon intensity of incident people? There is no absorption, it's not boundary, it's not a material which will absorb. It's just a boundary. Next. Now, people, what is the relationship between intensity and amplitude? Intensity is proportional to A square. Okay, good. So intensity of reflected, can I say is amplitude? No? Amplitude of reflected. What is amplitude of reflected, right? What is amplitude of reflected? C2 square. Reflected is C2, and incident is C1, and this
C3,
C3, and this is I1.
C1.
Okay, C3 square upon C1 square, correct? Because we are writing respective amplitudes. However, our coefficients, our constants are allowed to be complex, and they are complex also. There is a complex relationship, we don't know that as of now, but they could be complex. So just in case they are complex, I can write it as C2 star C2 and C1 star C1, and I can write this as C3 star C3 upon C1 star C1. I'm sure again if you have learned in your BSc, they have used this formula directly.
Yes, sir. Yes.
Okay, now you know why. Okay. So all that we have to do now is what we do. Express C2 in terms of C1 so that C1 gets cancelled. Express C3 in terms of C1 so that C1 gets cancelled. We will have reflection coefficient, we will have transmission coefficient, and we are done. And since you have two equations, can you try and do that? Express C2 in terms of C1, express C3 also in terms of C. Okay. Two equations, and we can do that. So you can give it a try. Otherwise, we'll complete this tomorrow. Don't worry, because we don't have time right now. So all you have to do is we have two equations, and you can express C2 in terms of C1, C3 also in terms of C1, and substitute it here respectively. Things will get cancelled. You will get reflection coefficient and transmission coefficient. And what is the rule, by the way? Absorption plus reflection plus transmission is 1. Anyway, there is no absorption happening, right? So reflection plus transmission should be 1. And you can verify that. So once you calculate this, add and verify. If you're able to do this by yourself now, then
Yes, sir. Then
try yourself. No problem. I will be doing this tomorrow in the class. But give it a try by yourself. Okay. Express C2 in terms of C1, express C3 in terms of C1. Substitute here. They will be real by the way. They won't be complex. So they directly substitute the squares. Okay. Just do that and see if you're getting the result. Okay. Just see if you're getting the result. I'm not sure whether you get the result or not.
Is our syllabus going to be completed on 30th of Jan?
Tentatively, because the timetable is also given until 30. And I told you, our score will be done. Our score has to be done. And I don't think I will require more lectures. So let's see.
Okay.
But by Saturday, let's see. Okay. So, you many people, thanks so much.
Thank you, sir.
No problem.
thank you, sir.
No problem.
Thank you, sir.
No problem.
Thank you, sir.
Arey, ek sath bol do sab yaar. No problem.
Sir, why are you telling it to everybody? No problem.
Well, if everybody is telling me thank you, it's my right to tell everybody no problem. I hate this practical, like even people when they wish on birthdays and individually, and somebody would just come up and write the status, thank you everyone for your beautiful wishes. I hate that, but I would be like individually, I need to tell them, like with their name especially. Like,
Yes, sir.
even when
Thank
they write thank you, even when they write thank you, I don't like that. I like thank you, Zainab, with the name. It feels good. They feel good. But anyway, chalo, stop.